these are the mundane phases of matter. There's sort of exotic things called like Bose-Einstein condensates that I don't know enough about to really talk about, but there are temperatures that are very, very close to absolute zero. But these are the four sort of mundane phases of matter. There's solid, it's like an ice cube, or this desk. You know, there we have it. And then liquid is, liquids and gases are both fluids. They can both flow, right? So if somebody says, you know, make sure you get enough fluids, just go, yeah, there you go, that's a joke, right? Okay, but liquids are things like liquid water, like what I'm drinking there. Okay, mercury is also a liquid metal, right? And then gas is gas, they're compressible and generally not very dense. And then plasma is most of the matter in the universe is plasma, right? Plasma is at such a high temperature that every collision knocks every electron loose. The electrons are there, but they're not bound to a particular nucleus. So it's sort of like they're at such a high energy state that the electrons are moving around, the nuclei of the atoms are moving around, and it's just chaos. Okay? Say it again? The sun. So when you look at the sun is a plasma. Every star you can see in the Milky Way galaxy, the part of the galaxy of the universe we can see that is not some sort of exotic dark matter that we can't see yet or detect. Okay? The part you can see, almost all of it is plasma, because if you look at our solar system as an example, the planets are minuscule compared to the sun. Yeah? Well, we're harnessing it right now. Can we have more quietness than that? Thank you. Okay. One interesting thing about plasmas is that plasmas, because the electrons are free from the nuclei, right? So ordinary hydrogen and helium, which don't ordinarily conduct electricity because the electrons are pretty tightly bound, right? They don't move from atom to atom. You know, plasmas conduct electricity like crazy because there's all those free electrons, right? So the sun is primarily an electrical thing. It's very magnetic. There's magnetic fields, strong magnetic fields in the sun. When you see those coronal mass ejections, those arc-shaped things that go up like that, those things are following magnetic field lines. If you look at them, they spiral. That's what charged particles do in magnetic fields, is they go in a circle, right? So look at those pictures. If you ever seen, I'm talking about those close-up pictures of the sun with the things shooting out of them, right? Those things are all spiraling because of the strong magnetic field of the sun. We don't really deeply understand what causes the magnetic fields, why they bind up every now and then, cause all sorts of sunspots and stuff. But
I don't know. So like, when static electricity is electrons no longer bound to a particular to go to another one. So.
Yeah, but minuscule amounts of them. Here's all the electrons, moles of them, right? Yeah. The question was static charge is they're not bound to a particular electron. There's excess charge, right? But we're just talking about a few million, or something like that, right? Or something like that, or a fraction of a mole, right? But here we're talking about many, many moles, thousands of moles. Question?
I was wondering if it's possible to achieve a plasma state on,
Oh yeah, sure, yeah. I used to use plasma on my sister, right? The question was, can you achieve plasma at ordinary, on Earth, right? What you do is you shuffle your feet across the carpet in the winter, right? You got to be quiet so your sister does not hear you. She's sitting at the table doing her homework, right? You shuffle your feet. In Minnesota, everything is very dry inside, right? And then you sneak up behind her and you touch her earlobe is the best, right? You touch her earlobe and that little flash of light that connects you electrically to your sister, right? Followed by a scream of pain, followed by a brief pursuit and the pummeling of your soft little body, right? Okay. But that little flash of light that you see, that little flash, that's plasma, right? So most plasma people do it with like arcs, right? It's very, very bright. It's very high temperature. Welders who use plasma, like arc welders, right? Those guys have to wear those really, really dark goggles or you get blinded. And if somebody is welding, by the way, don't look at it because you'll burn like a little hole in your retina. There'll be part of your retina that it's never going to be the same again. It'll be like, oh, look, that's neat. Oh, now I can't see, right? Okay. So here is a model. This is a solid. This is, by the way, a crystalline solid because the molecules are in a very orderly arrangement. There are other kinds of solid. Most of them aren't these pure crystals, but this is what we like to picture. And so if you think of the solid as getting hot, right, the molecules don't move with respect to each other. And as they heat up, they just shake more and more, but they don't shake enough to break free, right? But at some temperature, right, aren't they going to break free from each other, like ice will melt, for example? Okay. This is a liquid, right? In most liquids, here they're showing a lot of space between the liquids, but just think of greased marbles. They're going to sort of stay in contact with each other. Can you imagine that? Like a big bucket of greased marbles, stick your hand down in there or something like that, right? So they're just sort of sliding over each other, right? This is, by the way, what you're not supposed to do at high school dances, right? You're supposed to be more like a gas where you're rarefied and there's some space between you, right? Kind of a thing, right? But remember that these guys are moving a bajillion miles an hour. They are like those that simulation I showed you where the walls were shaking and those things were buzzing around. Remember that? Moving in straight lines at fantastic velocities, 4,000 meters per second or something like that, right? Okay, so that's a gas. Okay, the next thing, and this is a significant graph, right? The next thing is this notion that if we take, and this is water. How do I know it's water besides the fact that it says water on there? What's another clue that we would know that this is?
Degrees, it like stops.
Yeah, at 0 degrees, it heats up as a solid, and then at 0 degrees, it's making a phase transition, right? And then at 100 degrees, it makes another phase transition. Yeah, you guys have looked at this in chemistry, haven't you? Talked about that, right? Let's just talk about it. I don't want to talk too much because I want to get into solving these problems. Okay, but the notion is, and just draw this little graph in your notes, is that if we've got, and then just put 0 degrees Celsius, 100 degrees Celsius. It's helpful to draw a little line like that. People are amazed that I can draw those lines just so straight like that. You know? Isn't that amazing? Doesn't even go up or down or anything like that. I know. You can do, you could do this with chalk. I really miss chalk. You could take a chalk and just sort of point it forward, and it'll skip across the I know. It will. You can make dotted lines. It'll go brrr, like this. My calculus teacher could do that. It'd be like brrr, brrr, like this. Try it. Next time you're at a chalkboard, try that. Okay. So we heat up, and this is heat added. Right. So or if we're adding heat at a particular rate, like say 10 joules per second or something like that, right? This could be time, like that, right? But this is heat added in joules. This is our temperature in degrees Celsius, right? And notice that the ice heats up fairly rapidly, and then at some point it cannot go faster and faster. So at first it's gaining kinetic energy, right? And we would calculate the heat put in here using, well, MCAT, right? Q equals MC delta T. Then we melt. When we melt, there's another formula. Do you remember that? Do you remember the formula for melting? We don't remember this. Okay. So when you're melting, the formula is Q is just ML. Yeah? And L is another constant. It's like a latent heat. In this case, it's fusion. We'll talk about this in a little bit, right? Then you heat it up as water. This line has about half the slope. It's crazy. Slope is related to a specific heat, right? And then it is, this line here is actually 7 times as long as this line, right? About. So 1 time, 2 times, 3 times, 4 times, 5 times, 6 times, 7 times. They cheated on that graph, didn't they? Right? And then at some point, right? So we can draw these little regions in here, right? Here it's just melting, right? Why does melting take heat? Why does it take heat to melt it? What are you doing? You're not making them go faster. They're not going faster. Are they breaking free?
Yes.
Yeah, they're breaking little chemical bonds, right? So this is, in this region here, we're actually gaining potential energy, right? We're breaking little bonds, right? We're changing the position of the molecules. They're going from being bound together to being